Hello, everyone, and welcome to my webinar. Today, we're going to talk about the float mechanics. Um, we're going to talk about fundamentals. We're going to talk about some board designs, downfalls. We're going to talk about the smart designs and so on. So, to begin with, I'm Abdurrahman Fauzi. I am Egyptian. I'm very interested regarding aviation. I also play table tennis. I play every sport, but I'm not good at any one of them, I guess. I study petroleum and natural gas engineering, and I volunteer at UDSG. So, why do we need to understand the fluid mechanics? Because it is related to lots of aspects in our life. It's related to city water supply, agriculture, energy systems, and most importantly, to enhance sustainability. So, the moment that you use your tap water, the moment that you drink your mineral water, and so on, uh, the whole process is depending on the understanding of fluid mechanics. Same for agriculture. The apple that you eat at the morning is processed due to our understanding of fluid mechanics. Um, in addition to that, the energy systems. So we have the heating systems, we have the air conditioning systems. All depend on the understanding of fluid mechanics. Um, Furthermore, if we understand them like quite good, we're gonna enhance our sustainability. So we're gonna prevent, for example, leakage. We're gonna prevent friction. We're gonna also prevent the unnecessary loss of the of energy and the pressure. So this line is very important. The better flow equals less waste, and that's the power of the smart fluid systems. So the objectives of this webinar is to understand the principles of fluid mechanics, like the very basic principles. To understand how these principles, like to understand the pressure, flow rate, and heat and head loss, how they impact our daily infrastructure, how they work, and how they react. Explain the consequences of poor designs in piping and energy and so on. So how these poor designs are reacting and what is the main issue of these designs. And on the other hand, we're gonna understand the smart designs, why they are smart, and how useful they are. And the main focus is to inspire engineers, planners, and students of the importance of fluid mechanics. So we have some key concepts. The first thing is the pressure. So the pressure, I mean the internal pressure and the vapor pressure. So if you have a fluid, it's flowing within a pipe, then this fluid is probably pressurized. And you want to make sure that inside this pipe, this pressure, internal pressure, is lower than the pressure that you are applying. Like the internal pressure means the vapor pressure. So if the vapor pressure is higher, then this fluid is gonna vaporize if it is a liquid. And if it is a gas, it might explode. So you need to make sure to understand the pressure issues. Second concept is the flow rate, or we can call it the discharge. So the flow rate is the volume of the fluid passing per unit time. So for example, 5 liters per second. Why is it important? Because there is no fluid mechanical issue that you can solve without understanding this concept, the flow rate. We have the head. The head is implying the total energy that the fluid has. This includes the pressure, that the internal pressure of the fluid, the elevation, and also the velocity of this fluid. So all these three components affect our head, and as I said, the total energy is related to these three components. We have the head loss. So the head loss is the energy that you lose from your fluid. So for example, let's say our energy was, by the way, we calculate the head with the unit of meter, like in distance, because we consider it like, when you have the potential energy, it is always related to meters. For example, you have 5 meters, then you're gonna just say that these 5 meters from the ground, it means that I have this amount of potential energy because I have gravity. The same thing, we calculate it in meters in distance units. So if we have a head loss, this can be due to friction, the pipe roughness, the turbulence, and so on. We're going to describe it in more details. We have the laminar and turbulent flow. So the laminar flow is smooth flow, orderly flowing fluid. And we always try to have laminar flow within our pipelines. If you have an aircraft, you need to have laminar flow along the wing and so on. We don't need to have turbulent flow. And the continuity equation. Continuity equation actually make lots of sense, but you need to consider it because, again, in any fluid mechanical issue that you're going to deal with, you must consider this concept because it is literally the conservation of mass law. So, for example, you have a pipe, you have point A and you have point B. So if the flow at point A is 5 liters per second, then the flow at point B must be 5 liters per second as well. So how do we identify the poorly efficient systems? So we have two losses types. We have the major losses and we have the minor losses. The major losses are the losses that's related to friction. So one of these losses are due to the pipe length. I mean, this thing is quite universal because if you have, for example, longer pipe, if you have longer route, if you have longer wingspan, then you are actually dealing with higher friction. Same thing with fluids, all right? And also the pipe diameter. So if you have tighter diameter, it means that your flow is going to be faster. And as you know, if you are moving faster, then you have more friction. Same thing for fluid velocity. If it is higher, then we're going to have more friction. Same thing for fluid viscosity. If the viscosity is low, then you're going to have less friction. If it is high, then you're going to have higher friction. And surface roughness. So imagine now that you have a road, and this road is very smooth. And you have, on the other hand, another road that is like has lots of dirt, is not very smooth, and so on. So the friction that you're gonna face in the smooth road will be less than the road that is not well prepared. The same thing for the fluids. If you are moving inside a pipeline that has high roughness, then you're gonna deal with high friction. And then we have the minor losses. Minor losses are related to the disturbance of flow. So this disturbance can be caused due to the sudden expansions, contractions. Also, they can be caused due to the pipe bends and elbows, the valves, and the directional changes. And here are some examples where the minor losses happens. For example, here we have the contraction. So it was pretty big surface, now, as you can see. Then moving to tighter surface, then we have contraction. Moving to some directional changes in this area, then we're gonna have as well minor loss. We have an elbow here. We still have minor loss as well. We have contraction as well here. Again, minor loss. We have expansion. We have a valve. We have another expansion here. So this is how we determine the minor losses. The more of these components that you have, the more friction that you're gonna deal with, and the more energy loss that you're gonna have as well. And here are some illustrations. For example, this is an elbow, so the flow moves through the pipeline. But here's the catch. Why this disturbance happens? Because at the beginning we had laminar flow along this pipe, and then after this elbow, we are dealing with like discontinuity of the flow. So the flow was continuous on the surface, and here it discontinued, and this caused the turbulence. Same thing here as well. Same thing goes here. I think this is very useful explanation. And we're dealing with the most obvious indicator. So you can literally forget about anything that we talked about here because this indicator is very crucial. Um, you usually think of the friction that is caused due to the turbulence. So, for example, you have a turbulent airflow, you would think that the airplane is going to face high friction and so on. That's actually true. But in most cases, when the object moves inside the fluid, you're going to have some turbulence. This turbulence is caused due to the friction. So the friction is not caused due to the turbulence, but the other versa. Why that happens? Because as you know, the friction is like the fluid is applying force on the airplane, for example, and the airplane is also applying force in the fluid. So the air is gonna move, and this indicates that the airplane has lost some energy and made work on the fluid. And here's an example. Let's open the video. Okay. So this is an experiment that was made in the 70s, as I remember. So there's a vortex that the airplane usually causes when it flies on lower speeds. Oh, sorry. Yes. So this vortex that you were seeing here is due to the friction. So there is friction, and due to the friction, we had this turbulence, which is quite big, as you can see in the video. Again, look at this very turbulent flow. All right. So moving to the next slide. Okay. Now we're gonna understand the pumps and the pipes configurations. So pumps are usually they have two configuration, the series and the parallel. Each configuration has its own purpose and also its own characteristics. So, for example, in pumps in series, the flow rate remains the same throughout all pumps. Uh, However, the total head, like the total energy that's produced, is the summation of all heads that are produced due to each pump. So why do we usually use these systems with long distance pipelines? Because as we mentioned before, if you have a long pipeline system, this means that you are dealing with lots of friction, and then you need to compensate this huge amount of friction with big heads like these series configurations, and also the high-rise buildings. You need lots of head, lots of energy to produce. So you're going to use this series configuration. The mounted water supply as well, and the deep well applications. Because sometimes, for example, the wells might be 3,000 feet deep in the ground. So the internal pressure of the ground cannot really help you to make this fluid come to the top of the earth. Then you're gonna use a series configuration pipe pumps. Now we have the parallel pumps. They are connected side by side. So for example, there is the pipeline here. Then you have branches, and each branch has its own pump. The total head remains the same. So here in the series, the total head is summation, but here it remains the same along all pumps, meaning that, for example, if you have 3 pumps in the series configuration, you're gonna have 3 times more than the head that you have due to the same amount of pumps in the parallel configuration. And the flow rate here is summation of the individual pumps. Like, for example, each pump has flow rate of 1 liter, then you're gonna have 3 liters in summation. So as you can see, we use it when we need a high flow rate. For example, when you have city water distribution, you need higher flow rate. with low energy consumption. So you're gonna use parallel pumps for the HVAC systems, like the heating and air conditioning, firefighting systems, the wastewater treatment. Um, and here's an important thing: there is also a good characteristic about the parallel configuration, which is the redundancy. So, for example, if you have a system of 10 pumps, if one of them fails, the system will keep working. However, the issue is serious because they are connecting end to end. If there is one pump that stops working, then the whole system will stop working as well. And this is something that cannot happen when you have a city water distribution. You are providing water for thousands of people, for also air conditioning and so on, and wastewater treatment. This kind of fails cannot happen. Going to the pipes, we have three types: the circular, the elliptical, and the rectangular. So the circular pipes are the very common configuration. They are effective because they are very energy efficient, and also they can handle the highly pressurized fluids like natural gas, the water supply, and so on. And there's another thing: they require less maintenance costs than the other configurations because they can deal and endure as we said, the high pressure and the friction values more effective than the other pipes. Why is that? Because the pressure, because the T ring is evenly distributed against the walls. So, for example, you don't have some areas or joints that are getting like affected more others. Then you're gonna have to deal with lots of maintenance trouble. Now we have the elliptical pipes. Elliptical pipes are very similar to the circular pipes, but with the elliptical shape. Why is that? Because sometimes you don't have uh, area. So, for example, you don't want to dig deep on the ground under the ground and put your pipes. So you're gonna use this configuration. As you can see, the vertical height is different than the horizontal width. So the if you don't want to dig deep on the ground, or even if you have, for example, small width, then this pipe, you're gonna just switch it like that, and you have more efficient design for the limited area problems. So usually you can use them in stormwater systems if you have basins and so on when the height when the area is restricted. They also have very nice characteristic that they can handle pressure, because in rectangular pipes we understand that they cannot handle the pressurized fluids. Rectangle pipes, they are usually used for the heating and the air conditioning systems. Why is that? Because these systems are not pressurized. They have gases. These gases are not doesn't have very high internal pressure, so they are not going to cause lots of friction. They're not going to cause lots of tearing and then result into maintenance costs. This will not happen. So we use rectangle pipes for this cause, and also they are very area effective. Like they are even more effective than the elliptical pipes. You can implement them too easily inside buildings. That's why we use them. And now going to some smart application of fluid mechanics. We have the vortex-induced vibration. This kind of energy harvesting happens due to something called the Kármán vortex. And let's see how this vortex happens. Okay, so to begin with, if you have a cylindrical shape, and or even not cylindrical, maybe elliptical shape as well, and you put it like that, and there's flow goes against it, there's gonna be some wavy flow motion of the fluid. Let's look at it. like alternative um, wavy motion of the fluid. Look, for example, this is the fluid, which is air, and this is the cylinder that we have. After some time, it will start vibrating. If you increase the diameter as well, the vibration effect will be much higher as well. And this can affect also bridges because it works in the same way. It doesn't necessarily need to be a cylinder, even if it is rectangular, the same vibration will happen as well. So, why this method is very effective? It is very effective because sometimes you don't have good flow rate. You know, turbines need high flow rate of the fluid. So sometimes you have rivers, sometimes you have canals, and so on, tidal zones. So you don't have very fast flow rate. But also, it doesn't have blades. So if it doesn't have blades, then it will be eco-friendly, especially with fish in the water. All right. So how this system works, we're gonna see. We have a cylinder here. This is the cylinder here. Um, the water moves, so this starts vibrating up and down. And here's a generator, uh, and that's how we generate electricity. No turbines are needed, no blades are needed, and also no high velocity profile is needed. Second smart design is the fog harvesting nets. So from the name, you can imagine that these nets are working like fishing nets, but with fog. So the fog moves, and the fog carries the water particles, and the water particles will be stuck into these nets, and then they will precipitate down along this section, and then they will go along some tubes to the tanks, to the water tanks. Um, it is very effective because it can give you a huge amount of water. So, for example, the idle water participation is 3 to 10 liters per meter square. I mean, if you just assume that, for example, this is 4 meters tall and this section is 4 meters wide, then you're gonna have around 160 liters of water per day. Some nets may be very effective, like the ones in Morocco. They can yield for amount of 22 liters for each meter square per day, and they also don't use any energy, so it is totally passive. Um, and also, they can be implemented in houses as well. This is the map of the distribution of these nets. They are in Sandines, Bhutan, South America. They are everywhere. And this is how they can be implemented inside buildings. So we have kind of balcony here. You have these nets, and then you have again the area of participation. And we have a tube that's connected to the water tank. Um, same idea in this picture. You have these nets here, here. You have them connected to the water tanks. They are connected to the units that you have as well. So it's quite effective. And we have the storm water retention basins in Sofia, in Bulgaria. Um, so why do we use these basins? It prevents flooding. So, for example, if you have rainy day, instead of these water to be participated in the streets and in the neighborhoods, we're gonna cause them to settle down on the ground instead of implementing underground pipes. So I used to live in Saudi, and to deal with the rain, they used to have like massive underground pipes to collect this water and so on. I mean, the environment is quite different, but underground pipe is not very effective solution. And also it helps to recharge the groundwater. So I mean, it makes sense. You settle down the water, and then it enriches your groundwater as well. And again, it uses no energy. It's totally passive and turns green spaces into functional infrastructure. So instead of a place that's not used at all, you can just make it more efficient and you can make it part of your infrastructure. What are the laws behind, like the working mechanism behind these patterns? So we use the Darcy law. We use the hydrostatic pressure as well. We understand the water usually tries to move from the higher pressure to the lower pressure. We use the conservation of mass. As I told you in the beginning, we use conservation of mass, conservation of momentum, and conservation of energy to solve any fluid mechanical issue. And here's a picture. It is an illustration, it's not a real picture, but it shows you that this area is empty, unuseful at all. Now we could turn it into like a small lake. And also it will not help the groundwater as well. It will help the weather as well. Because, you know, if you have water surface and so on in the hot days, it will make things better, I guess. We mentioned about the porosity because, you know, these patterns must be porous. So how do we know if something is a rock matrix is porous or not? We use also fluid mechanics. We use the gas injection. And why do we use gas? Because gas flows easily into the tight zones and the tight pore spaces. It is also non-wet. What is non-wet? Uh, it's not going to stuck on the rock surface, and also it doesn't react with the rock. So it's a very effective way to calculate the porosity, and it also calculate the effective porosity. Why is that? Why we need effective porosity? Because effective porosity is the actual porosity that we can use, the pore spaces that can transmit the fluid. We have also trapped pore spaces, but these trapped pore spaces are not effective, and we are not interested with these pore spaces at all. Why this thing is smart? Because it is not destructive. I mean, if you have a liquid, for example, like water, and if it flows through the rock matrix, sometimes it can destruct and distribute cause some disturbance in the distribution of your pore spaces. It's fast as well and accurate, and it uses very simple concept, the pressure volume relationships. I mean, we use it in isothermal condition where the temperature is constant. So we just deal with pressure and volume calculations. No need to do some imaging, no need to do some drilling in the core log. Nothing complicated is needed. And this is an illustration of how it works. So we need to calculate the volume of this rock. We don't know the volume of this rock. We know the bulk volume, but we don't know the effective volume. So we use two chambers. One of them has the atmospheric pressure. One of them has 100 psi, and we again assume that it is isothermal condition. Then we open the valve, and the air inside is going again to the other chamber. The pressure is gonna decrease. It will not be 100 because it is distributed into two chambers. And then from these values, we can calculate the effective volume of the rock. Okay, so also fluid mechanics are related to airplanes. It's quite obvious. And also related to the sustainable flight. Boeing, I think in 2008, they have introduced the chevrons objects. So let me show you. These are the chevron objects, chevron shape. So this is the engine cover. These are the chevron shape ends. So why are they important? Because there is the engine exhaust, and the flow of this exhaust is quite higher than the flow of the of the air along the side of the cover. So we need to make some gradual like coincidence between the flow of the exhaust and the flow of the cover. If they are not similar, then this is gonna cause lots of noise and also drag as well. Um, but here's the catch. Why is this important? Because noise is very important factor in aviation. Nowadays, lots of laws are implemented against the engine's noises and so on. So now the aircraft manufacturers try to make this aspect more friendly, more sustainable as well. There is also downfall of this design. The engine effective thrust will be decreased by 0.5%. Why is that important? I mean, you would say 0.5 is not this high percentage. Well, when the airplane flies thousands or even millions of kilometers, this is gonna yield at the end like, massive amount of drag, massive amount of friction, and again, lots of fuel will be consumed, lots of costs. So this is actually very important. Percentage is not as low as we can imagine. It's quite effective. And also, some manufacturers try to minimize the amount of cockpit windows. Why is that? Because again, if you have lots of cockpit windows, this is going to create more drag. This is going to create more noise, and also will yield again into costs and less sustainable flight. However, this also goes with downfalls because it affects your fuselage integrity and the structural integrity as well, which means that you need to do more research in your materials to make it stronger and so on. Other manufacturers as well can have like six wing cockpit windows, but they gonna cover it with glassy and smooth structure. So it also reduces the amount of friction and also the amount of noise. We have the vortex. The vortex happens because when there is high pressure on the wing, lower, and there is low pressure at the upper side. That's why the airplane flies. So the high pressure sometimes try to creeps along the wing and reach the low pressure area. This causes this vortex formation that you can see here as well and here. And then we implement something called winglets, especially when your wing is actually short. This is for the narrow body airplanes. Usually have this winglet. It increases the range, it lowers the friction, lowers the cost, uh, less fuel consumption, and so on. How it works, it creates longer surface for this high pressure to move. And also somehow it creates wider wingspan. But this is not like the main purpose of implementing them. And we discussed that the vortex are something bad, but sometimes they are something useful. Why is that? Because if you look at this aircraft, you can find that this these wings are very swept back, and they kind of look like a delta-shaped wings. So to have a supersonic flight, you need to have sharply swept wings to the back. But this yields into very crucial problem. The lift in lower speeds, in landing speeds, for example, or taking off speeds, is going to be low. So we try to create these edges in a certain way that causes vortex to happen. So as we know that the vortex is literally the translation of friction, the amount of energy that you lost is going to be transmitted to the air, and the air is going to have lots of kinetic energy, meaning that it's going to be fast, which yields into lower pressure here, like even lower pressure on the wing. So this is going to enhance the lift at the end. Thank you so much for listening. I would appreciate if somebody has any question to answer.
Do you think that the fog nets can be implemented in other countries that don't have such a big problem with water? Basically, what I'm asking is it worth it?
So usually, if we can take the map, this technique is used in countries like Yemen, for example, because they had wars. Uh, yeah, as you can see, it is implemented in Yemen. It's implemented in Oman, some parts of Africa, because usually they don't have like the monetary resources to deal with the underground water. And also, you can find it with some South American countries because they have lots of elevations, they have lots of fog as well. But in my opinion, I would not think it would be very effective in countries like with high humidity, with good military resources. Like, I mean, the European side, some Asian countries, as you can see, there's like a scarcity of these implementations. So, in my opinion, I would not think it is kind of worth it. Maybe we can discuss it more.
Yeah, sure. I just saw Croatia on the map, and
Yeah, I think it hits something in your brain, like why Croatia? I think.
mhm.
Mhm.
Okay. Does anyone has questions?
But again, it is very useful technique because it uses like zero energy. It's totally passive. The only cost that you're gonna have is the production cost and the implementing cost, and everything else happens by naturally. So I think nobody has more questions.
Yeah, it is a bit out of the topic, but what do you think about wastewater reuse?
Go on.
Wastewater reuse.
Ah, so this I think we have some stations that I mean in Egypt that tries to process this wastewater and make it usable. I mean personally, yeah, I would think this can only be related to like normal usage for agriculture and so on, and tap watering. But for the human use, for drinking them, I would not think this gonna be a good idea. I mean, I'm not really aware of this topic, but this is what comes in my mind now.
Yes, in most of the countries, this water is used to water golf courts, to wash streets, to water the city parks, gardens, etc. Because to have machines clean the water so it's good for human consumption, uh, it's more costly. And the other thing is there is um, this way of thinking of people that
So, issue.
I'm not sure if the water is 100% clean or like I would drink water. But yeah, there are some good examples from Portugal, from Spain, and from Italy. And of course, like the island countries, Malta, Cyprus, in Greece as well. In the islands, they have a lot of them. I just mentioned it because
It's also related to fluid mechanics because I think the process of filtration will go the same way of the fog harvesting. Um, so it's quite related to fluid mechanics in my opinion, like the same way of filtrating. Mhm.
Yeah. Okay. Well, guys, if you don't have any questions, maybe we can close the webinar. Maybe we can stop the recording, and then if you want to like give feedback.
I'm gonna stop the recording now.